including the speaker and me. And I would like to, it gives me great pleasure actually to introduce today's speaker. Steve Koonin was the Undersecretary of Energy for Science a few years ago, but before that he was the chief scientist at a company that I'm sure all of you know, British Petroleum, as a major energy company. And before that he was the provost at Caltech. Most recently, he was director of the Urban Center at NYU, so he definitely has a few bits of experience that are relevant to the topic of today, urban energy. Steve, thank you for coming.
Thank you, Dave, and thank you for inviting me. This is my third visit to Cornell. The first one was just about 30 years ago, was also energy related. Those were cold fusion times, and the physics faculty here, applied physics, were interested in hearing me talk about that subject. The topic today is urban energy, and I want to talk about it in the slightly broader context of cities as a whole. We'll focus on energy in cities, but there's a bigger subject here. I went to NYU about 6.5 years ago when I got out of the government with the notion that I was going to study cities as a scientific object, the way in which a scientist or engineer would study any complicated system. The rationale is pretty straightforward. Cities matter a lot. They're where most of the people on the planet live today, and by middle of the century we'll see about 70% of the world's population in urban areas. The second rationale from an academic point of view is that the data are plentiful and diverse. We are seeing the increasing digitization and opening up of all manner of municipal and in some cases private records, and also the proliferation of sensors throughout cities, and there are things to do. And these are, in fact, the things that are the focus of the center that I just stepped down from as director a month ago. Develop technologies and methodologies to acquire, integrate, and exploit various forms of data. To understand the science of cities. Is there a commonality among cities or across time in a given city that we can understand in a scientific sense? And then finally, there are innumerable applications of that understanding in the governmental sector, at the citizen level, and in the private sector. So we were announced as, if you like, a runner-up or second place to Cornell Tech. I guess Cornell Tech was announced in November or December of 2011. NYU was announced in April of 2012, just about 6.5 years ago, as I said. There you see then Mayor Mike Bloomberg, all sorts of other dignitaries, and there I am in the back because I had no idea what we were going to do. All right? It was something about cities and data. And I think in the last 6 years we figured out some of what it means to instrument a city. It's good to think about it in terms of three buckets. It's always three. Infrastructure, the roads, the buildings, the utilities. The environment, not only the obvious temperature, humidity, but pollution, the flora and fauna in the city. And then the most interesting and in some ways the most problematic part of cities, the people. And cities are, after all, built by and for people, and you cannot understand them unless you can understand how the people are behaving, reacting, thinking, eating, etc. The notion that there is a lot of data out there, to just drill into that a little bit. First of all, there are organic data flows, the data flows that the city generates just in the course of doing its business. There are administrative records, census, permits, parking tickets, things of that sort. There's transactional data, sales, communications. There's operational data. How's the traffic flowing? Is the grid balanced? Things of that sort. And then there's social media. It's just out there. Cellular system is also something that's just out there in the ether, and if you know how to capture it, it has interesting information in it. Second, we're all carrying sensors around, the phones that we carry in our pocket, but there are video cameras everywhere. There are vehicle counters, vehicle trackers. We can crowdsource things now, and of course at toll booths, building entrances, all manner of data getting generated. And then most interesting from the point of view of a physicist and some of the people we're working with at CUSP are novel technologies. What can you learn by looking at the city as a whole in various modalities, all kinds of other currently exotic sensors for magnetic, for gravity, biological, and so on? Can you put all of this together to do interesting things with it, whether it's scientific or in a practical application sense? So the research strategy when I started the center, and Linda, these are some things we didn't get to touch on when we talked, so first, we were going to focus on the data. I mean, when we started the center, the people who wanted us to investigate new ways of doing concrete or building integrated PV, and I said, no, we're going to focus on the data. There's plenty to do there already. Most startups, whether they're commercial or academic, well, the commercial ones, academic ones never die, but the commercial ones die because they try to do too much. So focus. The second, focus on New York City mostly. A, it's because it's where we were. B, because New York City is quite sophisticated technically in the government staff. And frankly, C, the notion of having to deal with more than one city government at a time was just overwhelming. It takes a lot of effort at the legal front, the administrative front, to interact with the city and extract data from it. I also wanted to own the data. After all, there are many people who can access the open data sources, but I wanted to build a center that had an institutional familiarity with the data in its various forms, perhaps had differential access through partnerships in the government or private sector, and we could deploy unique sensor systems. And then finally, a strategy that I learned at Caltech is the facilities matter a lot. If you can create or find faculty who will create the world's first X or the world's biggest X or smallest X or whatever, that brings faculty together in a common purpose. It generates data. It lets you hire people and do great things. So there was a facilities and capabilities orientation. We started at the top level to think about a data facility, and I'll describe that more in a moment. Quantified community is another kind of facility, and then the observatory. Themes and groups, building informatics. Can we understand how buildings are operating? It's something that should be of great interest to you interested in energy. Mobility, obviously. Sounds, I'll describe that briefly, not directly related to energy, but certainly a quality of life issue. And then energy, as I said, and then a whole host of small projects having mostly to do with applications. The research themes, and I just want to go through this quickly because I'd like to get into some specifics. The energy in the built environment, building level energy demand, the structural integrity, social services, an important, not energy, but important part of cities, mobility, event and pattern detection. You know, cities happen every day, and they're more or less repeatable day by day, and when you start to measure, you see this diurnal periodicity with the weekends being slightly different than the weekdays, but pretty much everything looking more or less the same. So understanding norms and anomalies in that data is a really important activity, and then environment, of course, as well. So here's an example of the kind of records data or administrative data that's out there. This is a now somewhat old slide, but it gives you a sense of what data the city holds. So for example, transportation, fire department, finance, sanitation, and you can go around the horn. All of this data is only loosely federated in something I'd call a data heap called Data Bridge, and the city did not, and does not have the resources to clean up and integrate and exploit this data. So that is one of the modes that we were pretty successful in. There's also federal data that is available. This is from the ACS, the Census Bureau, in 2010, the American Community Survey, and is a map of the Gini index across the city. This is a measure of income inequality. I put it up not for the specifics of the map, but just to show you the granularity with which this data is available and updated. Okay, so let me talk a little bit of getting now into some energy topics. Constantine Contacosta, who's an assistant professor in civil and urban engineering at NYU, is deep in with the city records in energy and sustainability. And New York City passed a local law 84 about 10 years ago that required all buildings above 50,000 square feet to self-report their annual energy use. Electricity, steam, natural gas, heating oil, and so on. And there's been a lot of work now, Constantine and others have done, to try to understand the implications of that data for how buildings are using energy, and of course, can you do better? Here's an example. This is 1,150 office buildings in New York City. What's plotted is the weather normalized energy use intensity in kilobTUs per square foot per year. So it's a measure of the energy consumption scaled by the size of the building. And you can see, wow, some buildings use 4, 5, 6 times more energy per square foot than others. If you look at the apartment buildings, the residential buildings, the distribution is a little bit more normal, but there is still a tail at a factor of 3 level. What's doing that? Well, you can start to do analyses. Here's an example of, this is the EUI, energy use intensity, as a function of the year in which the building was built. And you can see that the newest buildings in the office sense use a lot more energy than the older buildings. So glass curtain walls are probably a factor here in energy use in the buildings. You could also disentangle the activity of the building, how the building is operated, the occupancy. All of these things can start to be untangled with this sort of data. You could also look at how energy costs impact the economics. This is a map of the energy costs as a function of, or as a percentage of household income across the city. And you can see, if you're focusing on the red and orange, in some of the poorer neighborhoods of the city, the energy costs are a staggering fraction of the household income. I may make a remark, just an anecdote. We got time, right? Yeah. I got to know a guy named Joel Spira about 10 years ago. Joel founded a company in his bedroom called Lutron. And Lutron makes 40% of the lighting controls in the world. And probably in this room. I think I see it back there. He did. Oh, Joe was here? Yeah, all right. Joe's a wonderful guy. Oh, right, okay. And we were talking about trying to get efficiency improvements in the office buildings in New York City. And if you look at it from the point of view of a tenant, your personnel costs are about $300 a square foot per year. $300,000 for an employee, all in benefits and all that, in a, say, a 300 square foot office, maybe 200 square foot office. Your rent costs are like a factor of 10 smaller than that, $30 a square foot a year. And then your energy costs are even a tenth of that, at the few dollar a square foot per year. And so nobody pays attention to energy efficiency in the commercial world. It's just in the business world. Industry is a different story when you're actually doing something. So it's really tough. All right, let me get on to a different topic and now start to use some of the sensors that are out there already. Okay, means the sound is working. That's good. Great. Starts to get into the quantified community discussion. Constantine and collaborators got access to a network of Wi-Fi access points in Lower Manhattan, about 20 of them spread out over a couple of blocks. And you may not know it, but when you walk by a Wi-Fi access point and the wireless on your phone is turned on, even if you don't attempt to connect to the access point pings your phone and gets the equivalent of the MAC address for the phone. And so you can, and Konstantin and collaborators did, just make a count day by day or hour by hour in July of 2015 of the number of pings by each phone. And you can ask, did I see that phone before? Do I see that phone every day? If I see that phone every day only during working hours, it's probably a worker. If I see that phone every day, but also in off hours, it's probably a resident. And if I only see the phone once, it's probably a passerby. And so you can do that hour by hour over the course of a month, and you see something that will become a repeating theme, the daily pattern. 5 weekdays, 1, 2, 3, 4, 5. A weekend, the balance shifts, the numbers change, and then again, weekday. You also see each day has a structure. People arrive in the morning, people coming out for lunch break, and then people leaving in the evening. And you could also see, let's see, the 4th of July is here, was a Monday that year, and you could see it also shows up low. So this is a way of getting a sense of mobility and traffic in the city at a relatively local level. Here's another example using found data. If you like, there are roughly 600 traffic cameras in New York City, and the feed from them is publicly available. One image every 30 seconds, I think. If you're inside the city, you can get it more or less real-time video, but this is one every 30 seconds. Greg Dobler and collaborators, whose name will come back in connection with some other work, wrote a neural net to analyze those cameras that have pedestrian crosswalks in them. So there's an example up on the top of 3 different scenes. You can see the zebra crossing in these, and in 2 of them. And in other scenes, you don't see pedestrians at all. And you're getting 1 frame every 30 seconds. It's not hard to write a pretty good neural net to just count the number of people in the scene. And so they did that, training data, and you get sort of interesting patterns. So this is upper left camera weekdays, just camera number going down, and time of day going across. Lower panel are weekends, and I guess the normalization of these 2 are slightly different. Anyway, again, as you see in the graph in the upper right, you get a pretty good diurnal pattern and a way of measuring flow of people going through the city. When you do this in Greenwich Village, you get a very different pattern than if you do it in Midtown, and again, if you do it out in the outer boroughs. So again, start to get some sense of the sort of basic physiology of the city. All right, then we started to do some things that put out our own sensors. This is not energy, but its environment is important. Juan Bello, professor in music at NYU, picked up this project which is called Sonic Sounds of New York City, which is to deploy a couple hundred sound sensors around the city and to analyze the results. So this is the box. It's got a fancy microphone that's good to 2 dB, which is the noise code enforcement limit. Microprocessor exfiltrates the data through Wi-Fi. I think it's about $85 a box, manufactured in China, and they've got a couple hundred of them. There's an early deployment of the box on a ledge above a street in Greenwich Village. You can see the power and data cable, sock covering the microphone, and of course something nobody ever thought about at the beginning, the pigeon spikes on the top. Okay. The initial deployment, you get a sense of what it takes to put these out. More than 50 nodes now deployed. They're taking 24/7 sound pressure level data, so not real recordings, but just dB measurements. They're taking random snippets of audio. So why is that? That's an interesting story. It turns out in New York City, you may not record a conversation on the street unless you're a party to the conversation. So you actually have to be there. That obviously poses a problem if you're trying to put out hundreds of sensors 24/7. It's a remnant of the wiretapping laws. Interestingly, you can record video, but you may not record audio. Okay. So we thought maybe we put a graduate student at the base of each microphone around the clock or something. No. And so what they want to do anyway is train up a machine listening algorithm so that you don't have to listen to the audio, and I'll show you that in a second. But the lawyers decided it was okay to take 15-second samples of the audio and use that as the training data. So that's what they were doing. I believe that's pretty well done now. And of course, this is all real-time telemetered back to a center. Here's an example of the machine listening that was developed. I think if the sound is working. Okay. So the classification comes up in the right way. Okay. Yeah, it's New York City, right? More New York City. Okay. So, you know, there is a, let's just get back to this. There's a whole system here to build that consists of the hardware, the software, the interaction with the enforcement people, the analysis. The software, the way the analysis is done is to convert the audio stream into a sonogram or phonogram, whatever it's called, time frequency display, and then do visual pattern recognition on the time frequency domain. All right, so that's going on. The environmental protection people at the city love it. It'll give a sense of where the violations are happening. It'll probably shift real estate values. You can look at health impacts of noise and so on. Please.
I'm just thinking this must be a conundrum, getting permissions to do this.
Oh, it's terrible. Yes. So my advice to people who are thinking about doing this kind of stuff is if you can avoid interacting with the city, just do it that way. All right? Okay. Yeah, that too. So I'm going to show you an example of that. All right? So other sensors now, and starting to verge on energy. When I started thinking about cities, now almost 7 years ago, I stumbled across this picture in the National Geographic, which is Manhattan taken in the thermal infrared. So we're now looking not at light that your eye would see, but in the heat radiation at 10 microns or so that are coming out. And if you look at this, there are a lot of interesting things to see and take away. One is that building turns out to be a residential building, and I can read the thermostat setting in every one of the apartments just by looking. That's pretty good. That building, we know what it is, and it's got a data center in it. And you see it's hot on the bottom, and the vents are hot on the top, and otherwise relatively cool. So I have correlative data that I can use to interpret what I see. And the third is, that's a set of, I can't remember which ones, housing projects from the city, low-income housing, and you can see it's glowing red, right? Because the heat's on and people have the windows open. And okay, it happens in the high-priced buildings also. In my NYU apartment, I got the same problem. All right, waste of energy. But look what you take away from that. It's a single sensor, some infrared camera, pretty sophisticated, but nevertheless, single sensor. It's synoptic in the sense that I can see 1,000 buildings at once. It's non-permissive. I didn't have to go in and put in a smart meter or a thermostat or ask people to fill out a survey or whatever. It's persistent. I get to watch all the time. It's not like a satellite where if you're lucky you get one look every 3 days, or an overflight where you have to pay hundreds of thousands of dollars for a few hours of coverage once a year maybe. And then it can be done with high granularity. You can see into the level of individual units. Right? So that seemed to me pretty interesting. And I was fortunate to find an astronomer, a guy named Greg Dobler, who had sort of gotten bored with the cosmos and was intrigued with what you might be able to do with astronomical techniques in this mode. And we now, over the last 4 or 5 years, have been doing observations in the visible, in the infrared, in hyperspectral, and hypertemporal. And I'll show you some examples of what you can learn from all of that, assuming we have time. Here's the view from the offices we were in until a few months ago, looking from northern Brooklyn into the east side of Manhattan. The Empire State Building is in the upper left, 3.8 miles away, just to set scale. A bunch of residential in the foreground across the East River, and a bunch of commercial in the midground. Lots of projects. We'll see some stuff about aerosol plumes. We'll see pollutants. We will do something about hypertemporal and the health of the electrical grid. So I'll show you. The first thing you have to understand is, what am I looking at? And we were fortunate to have a LiDAR topography data set of the city that shows the city elevation at 1 foot resolution, both horizontally and vertically. And you can imagine it's a relatively simple exercise in geometry to take an image and fuse it with that topography to identify the XY coordinates of every pixel in the image. Once you've got the XY coordinates, you've got the map, you go to the city database, which has details about every building in the city for tax purposes, and then you can understand what you're looking at. And here's the fusion of about 5 different data sets. That's the image I just showed you. It's color-coded according to the log of energy use intensity. So it takes the LiDAR topography, the tax data, the image itself, and the local law energy benchmark data to show which buildings are using more energy than others. Also outlined in black are those buildings that use heavy heating oil as their primary heat source, and that'll become important in another application I'll show you in a minute. You might ask, what are the hot buildings? Who's using the most energy? Turns out to be hospitals and recording studios, as you might imagine. They run more or less round the clock and do energy-intensive things. Here's a time-lapse video of the scene, 1 frame every 10 seconds, registered because the camera's moving in the wind. And through a night, what you see is that the residential lights going on and off, some flickering. The Empire State Building just goes off at midnight. I think the Chrysler Building goes off a little bit later. And then dawn, clouds, the sun moves through the sky, clouds start to come and go. You could predict PV output by watching the clouds just move across. Things of that sort. All right, what do you do with this? We started just by, because it's astronomers, you identify the sources. So they picked out at the beginning a couple thousand sources and just looked at the light curve for each window, or each source. Here's a typical one. I have no idea which window it is or which night it is. And you can see at 7 o'clock at night, the light goes on, goes down a bit at 9 o'clock at night, interestingly on the hour. At about 11:30, it looks like a light got switched off, somebody went to bed. And then maybe at midnight or so, the baby woke up, or there was insomnia, or who knows what. So record here of human activity. All our analyses are done anonymous and aggregated, so we're holding the privacy well. When we went to the IRB, the Institutional Review Board for Human Subjects, and we said we want to do this, the response basically is, why are you bothering us? Everybody looks in everybody's window anyway in New York City. Not quite this true. And actually, New York City has the highest per capita sales of binoculars and telescopes. So you can get, you can do this pulse of the city kind of thing. When do the lights go on and when do they go off? And you discover it correlates actually pretty well with the meter-determined energy use of the buildings. So this is an interesting, cheap way of starting to understand who's using what energy just by watching the lights going on and off. You can do interesting things with sleep-wake rhythms, but since you're an energy focus group, I'm going to skip that. We're starting to run short on time. During the day with these images, we were quite interested to see that there are things to see. This is about a 2 or 3 minute loop of during the day. And this is the background subtracted loop, where you take out everything that isn't changing, and sure, you see the traffic running along the bottom, but then you see this white blob coming up in the middle of the frame, like that. And we've colored it in over that. And of course, what that is that. Okay, not that particular one, but that's an example of it. The heavy heating oil, when the boilers fire up, they don't have the right stoichiometry, and they get this terrible black cloud. Biggest source of particulate pollutants in the city. Not the diesel, but it's this. And of course, the city's trying to get everybody to convert to gas. That's great. But meanwhile, we can watch. And the environmental protection people are interested. We can tell when are the plumes happening, who's doing it, you get a measure of the urban winds, where is it going, that sort of thing. Here's an energy use, again, just by watching. Your ordinary camera takes a picture in 3 colors, RGB. You can buy a device for about $70,000 that is a hyperspectral camera, that takes a picture in 850 colors. And so for each pixel, you get the spectrum, not just RGB. And this is a scan of the city. It takes about a minute or 2 to do this. And the different sources have been color-coded according to the different lighting technologies. So these are laboratory spectra of high-pressure sodium and LED, different kinds of LEDs and so on. And of course, this is the kind of thing astronomers love to do. You can match the spectrum of the laboratory sources. NIST has a catalog of them against what you see in the images to type each of these sources. So here's a blow-up of the Manhattan Bridge in the lower left, and you can see that the necklace lights are LEDs, and the road lights are high-pressure sodium, and so on. All of these sources I showed you here, this was done a couple years ago, are external sources, but we've now got the sensitivity that we can see, we can type the apartment lighting. And that's interesting from several points of view. If you're a manufacturer of energy-efficient lighting, you might know then who to target for your advertising. But also, we're working toward doing a natural experiment in rebound, in the Jevons effect. So do you all know what that is by now, right? Yes, okay, good. So if I'm watching your lights and I see that you've switched to a more efficient lighting technology, does your light stay on longer after you've made the switch or not, as a signal that there's some rebound or not? So we're not quite able to do that yet, but we're getting close. All right, more energy. Hypertemporal imaging. Federico Bianco is another astronomer involved with this. The mains current, or the mains voltage, oscillates at 60 hertz. And therefore, not every, but almost all lights are flickering at 120 hertz, right? I squared R is the power, right? So it's going to go at twice the frequency. Except it's not at exactly 120 hertz. The grid frequency varies a bit. And more interestingly, the phase of each light relative to others is not trivial. There's interesting science there, we think. And so we developed a way to basically analyze the flicker of these lights that you see in an image just by putting a shutter in front of the camera and other techniques. So here is such an image, a few minutes worth. There it is. Here's a source, and you can see it oscillating. Basically, the trick is to chop the image at something close to 120 hertz to downbeat the flicker to something that the camera can manage. In this case, it was about 4 hertz. And there is the image number, frequency. It's not exactly, as I said, what it is. So we're now able to do this remotely and watch the grid health. Let me show you this picture, which is more interesting. This is the grid frequency over, I don't know, 4 days, starting in July. And there's 120, and you can see it's not exactly 120. So pretty good way of monitoring the grid. Of course, the power company can do that already. But what's more interesting is that we can measure the phases of the sources as the load in each building goes on and off, or the transformer's age or whatever, and get a sense of grid dynamics and grid health that way. You may have heard about PMUs, phase measurement units, right? So this is a way of doing what the micro PMUs would do at much less cost and non-invasive and all of that. Good stuff. All right. 2 more, and then I think I'm done and we can do some questions. Thermal infrared imaging. This is an image from the Stevens Institute of Technology in Hoboken, looking at the west side of Manhattan in the thermal infrared. And there it is 2 minutes later. And you take the difference between them and you see what's changed. And well, you see here at the tops of buildings, they're burning fuel, and that's probably the exhaust from some gas or heating oil being burned. The traffic, of course, has changed, the river. But we got real interested in that. Right. What was that? Well, we've got building ID, and we identified it as a building on the West Side Highway. It's right near Google, for what it's worth. But what's interesting about that picture is you see the 8 cooling towers on top. And so we caught one of the cooling towers turn on, and it lit up as it got hot doing its cooling thing. So that's pretty interesting. I've now got a way to watch the HVAC operation of all of these buildings non-invasively and persistently. And in fact, here's an image or an analysis of an image where it was at a couple hundred yards, and we put the IR camera on the heating vent and off the heating vent. The red is on and the blue is off, and you can see quite clearly that the heating system is cycling, and sometimes it goes into double cadence and then single cadence and so on. Well, this is pretty interesting if you're interested in energy efficiency, energy use in buildings. You can sit on top of the Bank of America Tower looking out at the rooftops of all of Midtown and Lower Manhattan and just watching the HVAC systems operate. Probably interesting. All right, I think this is the last example, and then we can do for some questions. Not only did we do thermal infrared, but you can do hyperspectral in the thermal infrared. And I got some money from a rich guy to borrow an instrument that is manufactured by the Aerospace Corporation and owned and operated by the Air Force to sit on the west side of Manhattan and watch the chemical emissions of Manhattan for a couple days. All right? This is 128 spectral channels from 7.5 to 13 microns or something like that. And you see a lot of stuff. It's pretty interesting. So you can see Freon 22, chlordifluoromethane. We see a lot of ammonia and so on. The CFCs are, being phased out, but if you have legacy stock or legacy equipment, you can still use it for another couple years. So we're clearly seeing this stuff come out. And I think the last example I have, so this has got the ability to chemical type the plumes from the spectrum in the infrared. We saw, I think we need to run it. We saw every afternoon a hit on acetone coming out. You can see that black spot there. It's extraordinarily sensitive. As a test, we sent some graduate students across the river with a couple of cans of computer screen cleaner. and just let it loose, it's some chlorofluoro something or other. And boy, you could see it clear as day. These clouds just drifting up the river. So it's very sensitive. So we said, acetone, what's that, right? We thought nail salon, right? Nail polish remover. We had building ID, so we could determine what it was. We typed it as 677 Washington Street. It turns out to be 679. Couture cleaners. Acetone is used in solvent in dry cleaning. They do on-site dry cleaning. And so we could have a remote proxy of economic activity of this company if we decided to do that. I really wanted to find a drug lab, but it's probably the wrong neighborhood and not enough time. Anyway, we have an application in to the NSF to try to get an instrument to do this sort of thing. All right, a couple of points to close up. What's missing here? Data standards. We spend a lot of time cleaning data. Data ontology. There are 4 or 5 different ways of naming a building in New York City. People, organizations, how do you describe all of that in a data sense? Data hoarding is a real problem. I like to say the second most basic human urge is to hoard data. The academics do it for priority, right? The companies do it because it's valuable, and the government does it because they don't want to be embarrassed or they want leverage in the government. So bridging these data walls is not so difficult. For a lot of the things we and others are doing, who are the customers? City governments are tight budgets. They're generally not technically forward-looking. The firms are trying to figure out how they can make money with this kind of stuff. And of course, citizens, you would think, are customers, but they generally don't pay for things, at least at the individual level. Citizen acceptance. Since we started this, privacy has become a much bigger concern. There are concerns about control, being manipulated in various ways, and we all are already, but this makes it even more real. And then somehow engaging people much more in this. This is not just an engineering problem. This is about people. And so it's not going to be the optimum in the engineering sense, whatever we come out with. All right, thanks for your attention. I think we've got 7 or so minutes for some questions or comments. I'm happy to hear what you all think. Thank you.
Let us have some questions. Yes, please.
Do the infrared picture that you take help you understand energy consumption in any quantitative manner?
Yeah, that's a really good question. I think doing the absolute, if I could measure the absolute temperature in some apartment, that's not particularly useful because I don't know what the insulation's like and so on. But it's the persistence gives you a self-calibration in the sense that you can look, is it 20% higher than it was last month or something like that. So it's that kind of internal calibration, which is quantitative in a relative sense, but not in an absolute sense, I think is very useful. That's true of all these persistent things, right? You get the time base helps an awful lot. Yeah.
I'm just curious, what type of funding agencies do you work with to get funding for your research?
So it's not so easy. The NSF has got a program, and Sonic and a couple of others. RPE funded some of the observatory work. DOE, the main parts of DOE do some funding, but there is no, how to say it, there's no Department of Cities. You would think Housing and Urban Development would be that, but no, not much, no. So, yeah.
So one of the things that caught my attention with the infrared image in particular is just how buildings that are geographically, very close to each other, similar time of day, but how different they were.
Yeah.
And I wondered about that. Is that something to do with the construction? I mean, because those sort of stark differences are often a way to identify major changes that could be made for efficiency and so on.
So the first thought, and we don't have a quantitative, we have not managed to hook up the records data with the infrared yet. It's probably building facade, and right, and maybe the way the building is operated. But there's another effect in the infrared, which is, I think, a rich area for applied physics. You know, the buildings are all radiating and absorbing simultaneously with one another. And you get these urban hole realms, right? Sunlight comes in here, it's radiating there and there. So doing that, the radiative transfer calculations, together with the measurements and so on, I think is a really interesting area. People have done some kind of, you know, simple Wigner cell-like, you know, one building periodically repeated and put the sun up here and so on. But real measurements with real modeling, well within our technical capabilities, but just not done yet. Okay. Yeah.
Yeah, so I'm curious as to if there are any governmental or non-governmental organizations that are heavily interested in using this data for things like, I guess, to sort of look at things like whether like compliance, like monitoring compliance for air quality issues, because EPA essentially doesn't even regulate smaller sources.
Right. So you can go out now and do really dense measurements, right? Whether it's in situ particle meters or this kind of synoptic stuff. Not a lot of interest. Yeah, data's there, you would think, right? I should say, you know, there are sort of three broad uses of the data. One is the shape of the haystack, if you like. Broad trends, this kind of diurnal pattern I was showing you, geographical patterns. The second is the needles in the haystack, which is the compliance discussion, and there are many examples I could give you of how the data can help at least cue compliance enforcement, if not do it directly. And then the third is to validate and calibrate predictive models. So if I put in a new building here, how do I stress the electrical system or the rubbish collection or whatever it is? Basically, those are the three areas. Yeah.
You mentioned autonomous and connected vehicles, so I'm curious as to what sort of data you already have to monitor that stuff, and if you have any projects that are meant to sort of anticipate the future needs of those types of systems.
Yeah. So we have a faculty member that we hired now 2 years ago from Maryland. He's a geographer, okay? And what did I know about geography? I hated it when I took it in school, and you think it's all about maps and all that stuff. No, this guy, Paul Torrens is his name. He's a professor in computer science in NYU. He does models of crowd flow and generally the way in which the geometric environment influences behavior. So he's working with one of the auto companies to be able to acquire and exploit high-resolution scanner data from the scanners that'll be on the vehicles to help in vehicle control and navigation and so on. It's a lot of data when you think about it. We get the scanners down to about $1,000. We'll start to be able to acquire a tremendous amount of that, not only for positioning and so on, but you know, if there's a parking lot attendant that's trying to direct the car, can the scanner recognize those gestures and do whatever it's supposed to do? Yeah. It's very interesting. Yeah.
So are there limits to what you can do with these data, because you'll get into trouble because you're going to tell people they shouldn't be doing stuff like the EPA? I mean, have you thought about that?
Not very much. I mean, we already have that to a limited extent in red light cameras and things like that for compliance. You're talking about, you know, catching violations after the fact or before the fact? After the fact, yeah. I mean, it's just being able to do compliance much better now than you could before. And so you get into issues like, you know, what's the red light camera setting going to be? How much slop will it allow in the speed? That sort of thing. But, you know, in general, as a technologist, those things are above my pay grade, I think, and they're really policy issues that my opinion is not particularly useful. But we can do these things. The question is, does society want to do them?
How easily could you apply the spectrum method to, let's say, find a gas leak in a methane?
So, I had a slide on methane detection. We can see methane. And we think we can see it at useful levels in the sense of detecting meaningful leaks. But there are already so many companies out there already that are doing in situ drive-around sensing that it's just not something that we can profitably pursue. But yeah, we can see it.
Well, I think that does a good job of answering all the questions that seem to be here, but I do want to remind you that all of you are invited to come to 116 Upson Hall, is that right?
Yep, that's right.
To pursue further questions and even get a little bit of lunch. So we do invite you, faculty members, a few more students if you're a student. Thank you again.
Okay, good.